So, why do that?
Way to go, Fred.
Bring it back. All right, good. It's recording. So, hopefully you guys can see these little pitballs. These things right here are called pitballs. They are pieces of styrofoam that are coated with, I think they're coated with graphite, and that makes them conductors of electricity. So when they coat with graphite, then they can transfer charge really easy. So I'm trying to make it so you guys can see what's going on. So I'm charging this rod. I'm bringing in this pith ball, and you'll notice that the pith ball is attracted. You guys see that? You guys see how it's following the rod? Okay, once again, physicists are magicians. Okay, a lot of displacement here, right? So I put it here in the middle. Both are attracted. So what that shows us is that both of these, actually I'll pop the rod out. The glass rod with cotton. Okay, bring it back to the middle. Shows us that you see they're still attracted to it. You guys see that? So since it's attracted to both positive and negative, that means the pith balls are neutral. Okay. Now, how do the pith balls know there's something by them? Do the pith balls have eyes?
No.
The pith balls don't have eyes, do they? How do they know there's a charge near them?
The sixth sense.
The sixth sense, they have no senses. They have no eyes, ears, nose, mouth, whatever. So they don't have six senses. They don't even have five senses, Sergio.
They have one sense.
So how do they know?
The sense of,
Because of the electrons.
Because the electrons. So the electrons can see?
No, but they move.
No. How do the electrons know? Tony, I heard you say something. You said something. I heard it. What'd you say, Tony? Say it again. You didn't say anything. Someone said it. Okay. Let me charge one of these pith balls.
magnetic.
Okay. You see how it bumped into the rod and I saw it on there? But now that pith ball is repelled, right? Because when it touched the rod, what kind of charge did it get? Negative. So if I bring that pith ball close to the other pith ball, oops. If I bring it close to everyone, come on, let's work today.
There you go.
They should be attractive, but they're kind of. Okay. You kind of see it wiggling towards it a little bit. All right, you see that? Okay. When to charge the other pith ball negative. Okay. And now it's attracted. The strings are entangled. Oh, I got a little laboratory science. All right. So now you might see that there's a little bit displacement. You can see the cords. The cords aren't hanging straight anymore. Wow, that one's wiggling pretty quick, pretty crazy. All right. But how do these pith balls know that they're repelling each other now? Can they see the charge on each other? No. How do they know? How do they feel the force? How do they know there's a force there? There's something surrounding each pith ball called an electric field.
Message from Esther Sizer.
Really? All right. I'll put that on silent, please.
Wow.
There's something surrounding the pith balls called an electric field. All right. An electric field is a region of space that is affected by electric charge. All right. So if you have notes, you might want to take this out.
New message from Esther Sizer.
Did you not hear that the first time?
I don't think so. All right. So electric fields. They are created by charged objects. So when I charge the pith ball, when I charge the rod, surrounding the pith ball and the rod was an electric field. Okay, that's okay.
No, it's okay.
It's okay.
It's embarrassing.
It's all right. No one else saw. But now YouTube knows what it is. All right. So, there's only two E's in electric. Well, I do, but not right next to each other. Electric field. Okay. So, an electric field is the region of space surrounding an electrically charged object. Okay? In that region of space, any charged object will feel a force. Okay? So, electric fields are the space surrounding a charged object. Okay? The space surrounding a charged object. And any charge in an electric field will feel a force. Okay. So the fact that those two pitballs were feeling a force from the charge rod I created and feeling a force from each other, that indicates to me that there was an electric field surrounding the charged objects. Okay? Because something felt a force, that tells me that that charged object was in an electric field. Okay, does that make sense, guys? Because because the pitball felt a force from the charged rod, we saw the pitball attract the charged rod. That tells me the pitball was in the electric field because it felt the force. Okay, does that make sense? Guys, does that make sense? Okay, if something feels a force from a charged object, that means that something is in the electric field. Electric fields produce forces that do work. Okay. They produce forces that do work, and they can also be used to transfer energy. Now, Sergio, if I were to charge that rubber rod to a stronger charge, to a higher charge, okay, so I had more coulombs of charge on that rubber rod, would it apply a bigger force or a smaller force to the pitballs? A bigger force, right? So do you think the electric field would be stronger or weaker? Stronger, right? So larger charges, meaning more coulombs, larger charges mean stronger E fields. So larger charges mean stronger electric fields. That's fine.
So, Mr. Branch.
Yep.
Electron is small e and an electron is big E.
Yep. Got a question, Moses? I'll change seats. Okay, are there any questions about E fields? All right, so any charged object will produce an electric field. Right? So when you charge balloons, they produce electric field. And the amount of charge that object has, so the bigger the charge, the larger the electric field. Come on, Prezi. Here we go. Maybe. What? You can go outside. Awesome. All right, we'll go that then. Let's say I have a large charge, it's positive. Okay? And I take two little charges and I put them near this large charge. Okay? So I have a large positive charge. And now Prezi wants to work. So I have a large positive charge, and I put these two little charges near it. Okay, I'll call these charges, we'll call this one Q1, we'll call this one Q2. All right. Which charge, if the two little Q's are the same charge, they're the same magnitude, which one will feel bigger force?
This one.
So, big Q is some large charge. You can think of it as like 10 coulombs. Some huge charge. Okay? Each little q is a small, we'll call it a proton, a single proton. Okay? Which little q will feel a bigger force, Q1 or Q2?
Q1.
Okay, Moses, you said Q1. Why Q1?
Closer.
Okay, it's closer. So Q1 will feel a larger force from the big Q because it's closer. Does that make sense, guys? Yeah. If Q1 is positively charged, which way does it feel that force?
Towards
Away, right? If Q2 is positively charged, which way do we feel force? Away, right? So we'd feel two forces away if those two charges are positive. Does that make sense? Makes sense. Okay. What if I were to change this big Q to a negative charge? Okay. So instead of being a large positive charge, let's say it's negative 10 coulombs. Okay. Then which way would the Q's feel force? Towards big Q. Okay. I think I do that vector too long, too much shorter. The force is smaller. Right. But now they'd feel a force towards big Q. Which one is going to feel a bigger force here, Q1 or Q2? Q1. Why? Still closer. Right? So those two little Q's, if they are positive charges, we know if we have a positive charge in the middle, they get forces away, right? Right? If we know it's positive charge in the middle, if we know this is a negative charge here, then they feel forces towards. Okay? Now, an electric field is defined, the direction of an electric field is defined as the direction of a force felt by a small positive charge. Okay? So, electric fields, they are a vector. When you say E fields, they are a vector. Think of them as a vector field. There's a bunch of vectors all over the place. That's what an electric field is. All right? So if I'm talking about the electric field surrounding this Q, this negative Q, if I put a positive charge anywhere around this Q, which way will it feel a force?
Wait, repeat that.
If I put a positive charge anywhere around big Q, which way will it feel a force? Towards. If I put a positive charge anywhere around Q, it'll feel a force towards it. And as you move away, that charge will get less, right? Okay, so you have a little small vector because I'm far away, right? As I get closer, the force gets bigger, so my vectors get longer the closer I get. Okay, so back here might be a smaller vector. But every positive charge that I place in this area in the electric field of this Q will feel a force towards big Q. Does that make sense? Okay. If I were to switch Q back to positive, what's going to happen to all those vectors?
They're going to turn back around.
They're going to turn back around. Go the opposite way. Right? So, because now if big Q is positive, a positive charge will feel a force away from it. Okay? So what we've created here is something called a vector field. It is a field of vectors. It shows us the direction of the electric field at all those locations. Does that make sense, guys?
Yes.
Okay. Now, the direction of an electric field is defined. Now write this down. Direction of an E field, I'm just writing E, is the same as the direction of a force felt by a small positive charge at that location. So if you need to figure out the direction of electric field points, you just think about if I put a positive charge right there, which way would that positive charge feel force? And that's the direction of the electric field. Okay. Does that make sense? Any questions?
Can you do an example of that, Mr. Mark?
Yep, we're gonna do plenty. We're gonna do plenty examples. Okay.
On the bottom?
Yep. Okay. We always want examples. It's like you want to learn. Yeah. Calm down, Kim. Tim doesn't want to learn. He just wants to hang out. Right? Yeah. Turn up? Let's turn up on education.
No.
Yeah.
He said no.
Alright, so here's the drawing that I did on my own just a second ago. That's what I was trying to get pulled up for you. Basically the same thing we talked about. Alright.
Let's see. How's it charge at the location?
Yeah, at that location. So make sure I got all my questions. If both Q's are positive, which Q feels a greater force? Okay, we got that. Alright, so electric fields. So this is a positive charge. Okay? The big red thing is the charge. Positive charge. The purple lines are the field lines. Those are the directions. If I were to put a positive charge in the field, that's the way it would feel force. Right? So if I dropped a positive charge right here, which way would it feel force? To the left. If I dropped a positive charge right here, which way would it feel force? Oh, what about right here?
Right.
To the right. What about right here? What if I drop one right here? Diagonal. So just because there's not a field line right here doesn't mean the charge wouldn't feel force there. Does that make sense?
Yes.
The field lines are just representations of the field strength. Okay? There's 4 field lines. If I were to have 8 field lines, so if I were to draw another field line here, another field line here, another field line here, another field line there, what would that tell you about this charge? Is it stronger or weaker? Stronger. Okay. The more field lines means the more charge. Okay. So if I were to add field line here, field line here, field line here, field line here, then I would have created a stronger field. Then this charge would be twice of what it was. Because now I have 4 lines instead of, or not 8 lines instead of 4.
And you can just keep adding on to that?
Yep. If I added 8 more lines, then that would indicate that the charge with 8 more lines, so 16 total lines, has twice the charge of the one with 8 lines. Does that make sense? So more charge, you get more lines. And the reason being is the density of field lines. So the density of field lines, so how many field lines I have in that area indicates the strength of the field. More field lines means stronger field. So more field lines equal stronger E field.
Mr. Martin.
Okay. Yeah.
So what if electron on the field line?
Okay. Field lines are only pointing the direction a positive charge would feel, right? So if my field line points to the right, a positive charge would feel force to the right. If I were to drop a negative charge in here, which way is it going to go? A left. Electrons will always move in the opposite direction of the field lines. Okay? Because electrons are negative, field lines are drawn in the way a positive charge would feel force. Okay? So when I switch this charge to a negative charge, what's going to happen?
You're going to go forward with the circle thing.
Man, it's like you did some reading before you came in here, Sergio. Okay? The field lines are now all pointing towards the charge. Right? Now this one only has 4 field lines, so it would have an equal magnitude as the previous one, just an opposite sign. So the previous one was 2 microcoulombs. This one would be negative 2 microcoulombs. Okay, does that make sense? Okay. Now if I add 4 more lines, my 2 microcoulombs then becomes stronger. So if I add 4 more lines to this, I would have how many microcoulombs?
8.
No.
Wait, you said
I'd have 8 lines, but if 4 lines meant 2 microcoulombs, 8 lines means
16.
no, 4 microcoulombs. Okay, so if I add more lines, and since this is a negative charge, positive charge would feel force towards the negative charge. That's why the field lines all point into the negative.
What did you say the lines mean again?
Yeah, I don't.
The number of lines indicates the strength of the field.
No, we said something about microphones and
Yeah.
Okay, if this was a 2 microcoulomb charge, and I had 4 field lines, right?
I thought you
If
said
I-
it was negative.
Okay, yeah, it is negative 2. If I have a negative 2 microcoulomb charge, I have 4 field lines, right? So if I double the charge, if I double it to 4, instead of 4 field lines, I now need 8 field lines. Okay, more lines means stronger charges. Okay, and they're proportional. Yes, Richard.
Why do you have those if you said they can be like anywhere?
What?
Why do you have the lines if you said they can be anywhere too?
Because if I draw lines going everywhere, it's going to take a lot of marker, right? And it gets very jumbled. If I draw every single field line on here, I'm just going to have a solid black circle surrounding it. Okay? This is just a representation of the field at that point. So if I were to drop a positive charge right here, Richard, which way is it going to feel force? And don't say it won't. It's going to feel force towards the center. Okay?
Does it matter how many lines you draw?
The number of lines it indicates the strength of the charge. More lines mean more charge.
Oh, so it has nothing to do with where that is.
Right. So now if I drop another Q right here, is it going to feel greater force or less force?
Greater.
Greater force. So close to the charge, right? Coulomb's law, radius is smaller. Also, if you look at the density of the field lines surrounding it, the field lines surrounding this charge are closer together. Right? More field lines, stronger field. More field lines in that box, right? Stronger field. Okay, does that make sense? Okay. Any other questions? Now, what happens if we have a positive charge next to a negative charge? What happens? Well, the field lines point out of the positive and where? Into the negative. If I were to put a positive charge right here, it's going to feel a force which way? Towards the negative. Right? If I were to put a positive charge right here, which way would it feel force? Towards the negative. Okay? If I were to put a positive charge right here, it's going to feel a force towards the negative. If I put one up here on top, same thing. On the bottom, same thing. Okay? Coming off this backside,
Watermelon.
same thing. Coming off the backside right here, same thing.
Butterfly.
Okay? Guys, coming around the back. Goes around the world,
It comes back and hits it.
comes back right there. Okay? Does that make sense? Okay. Now, since, guys, I know I got short time here. What?
It doesn't flow.
I don't know what you said.
It doesn't flow all the time.
What do you mean?
Like if you have lines.
No, if I put a positive charge here, it does not go that way. Okay? Because the field lines, guys, stop talking. Okay. The field lines point in the direction of force felt by a positive charge. Right? So if I place a positive charge right here, it's going to feel a force that kind of arcs it towards the negative charge. Because the positive charge is going to push it away on a straight line, but then the negative charge is going to pull it in, so that vector addition is going to cause the path to curve.
But if you have negative, coming up from the negative, then isn't it going to positive?
Right, but the field lines only point in the direction of a force felt by a positive charge. Okay? So I talk about negative charges, they go in the opposite directions of the field lines. Okay? Now, this field, if I look at this region right here, we'll call this A, and I look at this region right here, we'll call this B. Which region is stronger, A or B? A, because it has more field lines. Does that make sense? Now, since my positive charge has 4 lines going out, my negative charge has 4 lines going in, what do you know about the magnitudes of these charges? They're the same. This could be 2 microcoulombs, and that one is negative 2. Okay? If this was 2 and that was 4, there would have to be more lines coming in to that charge. It wouldn't be all just from this one. Okay? Does that make sense?
Yes.
Okay, are there any questions about field lines? Any questions? Kim, don't worry, we'll get more practice on this.